The one theorem in this section is Theorem 4.1.2. It says that suppose that U is n-dimensional with basis B, with vectors u1, u2, un. So n means n-dimensional. And let L be a list of vectors v1, vn, any list of n vectors of v. Then there is a unique linear map T mapping from U into V such that T of Ui equals to Vi for I going from 1 to n. So what this theorem says, the uniqueness is important, of course, and what's important is that all you have to know is what you have as an image for the basis vectors. So with other words, to specify a linear transformation, all we have to know are the images of the basis vectors. So typically, when you have a transformation going between vector spaces, of course there are infinitely many elements in both vector spaces, typically, unless it's a trivial zero vector space. But if you have finite dimensional vector spaces, although they have infinitely many elements, we have a finite basis. So you have u1, un. And what this theorem says that if you know where this u1 goes, it goes into a v1, which is the image of u1. And then you know where un goes, it goes into vn as the image of un. Then you know everything. You know what the map is. So T is a linear map, and somehow we know how to specify it. So the proof is simple. You already saw linearity and vector space properties are very closely related. So we just choose let U be any vector in U, and because we have a basis B, that means U can be written as the linear combinations AI, UI with the basis elements with unique scalars AI. In the field F, I going from 1 to n. Since B is basis. So then what we do is we define T by the formula TU. Well, for linearity, if you apply it to the sum, it's supposed to go term by term, and then the scalar is supposed to be factored out. So if we need this, then let's define it that way. That it's the sum of AI times T of Ui as I goes from 1 to n, which is then the sum of the Vi vectors that we already know that has the image as the image of Ui under T. For linearity, it's easy to check. So if you have AB from F, and then for all UV vectors from the U vector space, because again B is a basis, that means we should be able to write U as well, I have to use a different notation now for V, because the V's are reserved for the notation of the list of vectors from the V vector space. So let me use W. So U should be written as a linear combination of the basis vectors. Then W should be written as some kind of linear combination of the basis vectors. Again, this is because B is a basis in U. Then let's check what the image under T of A times U plus B times W is. We don't know if we can separate it. We want to show linearity. We want to check linearity. So right now all we know is the definition of T, but T is defined using this linear combination. So first we should write U in this form, in the sum form. Also W in the sum form, in the linear combination form, using the basis vectors. The definition of T is using the sum with the coefficients So what we have to do for this definition to work, we have to combine these two linear combinations into one linear combination. So that will be A times AI plus B times BI, multiplying the UI vectors and add it together. And once we have that, then we get this definition with the V vectors. So now we can use the definition. Let me mention here that this is the definition, by definition. Now we use the definition that says that once you have this summation, then the result is supposed to be the coefficients, the scalar coefficients, AAI plus BBI. And instead of UI, we're supposed to switch to VI. So now this is in V. And since V is a vector space, we use the vector space properties that we can separate this back into separate sums, and we can factor out a constant multiplier with the V vectors. But then it turns out that this is the same as the definition of the transformation for U times the A scalar multiple, and then the scalar multiple of B with the transformation of the W vector according to the definition. But now we are using it backward. We are going from right to left. And then comparing the beginning and the end, we get the linearity. So of course the funny thing is that the book mentions at this point that clearly T is defined uniquely. Clearly means that it should not be difficult to show, but let's anyway show that T is uniquely defined. So for uniqueness, we assume S is another transformation with the property, of course, that was a part of the theorem, that we're supposed to have that the image of UI is VI. So this we know, S of UI is VI. So is it possible that we have another transformation? Well, then for any U vector from the vector space U, we check what's the difference. So we write again, of course, U as a linear combination of the basis elements. So we want to see what's the difference between the two transformations when we apply it to an arbitrary vector U. The difference between the two, that means T of U minus S of U. Now for T of U, we defined it as the linear combination of the VI vectors with the same coefficients A. S must be linear. That means that we can apply it term by term, and we can factor out the constant multiplier. So then we get S of UI, but then S of UI is defined as VI according to the assumption. So what we end up is AI VI minus AI VI, I going from 1 to n. These are the same, so this is the zero vector. We don't have to assume any basis property of V. Simply these are just the same thing subtracted. So that means that there is no difference between T and S. That means S equals to T, which is unique then. So many times we will work with linear transformations. We introduce the notation set of all linear transformations from U to V. It will be denoted with L parenthesis UV. Or with set theoretical notation, LUV is the set of transformations going from U to V such that T is linear. So what we saw before is, for example, that zero mapping is a linear transformation between arbitrary two vector spaces. The identity is a linear transformation between the space U into itself. Actually, the notation for that is just 1 U if you want to shorten the notation. There is no reason to duplicate that. And then the interesting thing is that itself, this set is a vector space. So if you have two transformations ST in this set, so then we have the sum transformation applied to a vector U is just the sum of the individual transformations applied to U. So this is also in V. This is well defined. Then the scalar multiplication is defined. The scalar multiple of a transformation is a transformation where the effect of that new transformation on a vector u is you simply scalar multiply the original transformation applied to u. And we also have the regular properties of vector space addition and multiplication, which means that we have a distributive property of scalar multiplication, for example. We also have commutative property of addition, for example. And we also see that we do need, for example, the identity, addition identity, the zero vector. So the zero vector or zero mapping added to any map, that's just the map itself, since it equals to the same effect as the map would be on any vector u. One way to look at this very nicely, how this space of linear transformations is a vector space. When we have from Rn to Rm, the n by n matrices transforming n vectors into m vectors. Then of course we have that if you have another matrix which is also n by n, that also maps from n, Rn to Rm. And then of course we can add together the vectors a plus b, and then the multiplication goes, the vector multiplication goes term by term, and also the scalar multiplication of the matrix is the same as the scalar multiple of the matrix vector multiplication. If we have these transformations going between u and v, from u into v, so we have all these transformations that are linear, then we can also continue and go from v into a third vector space w, and we look at the linear transformations going from v to w. Then we might want to combine together transformations. For example, if we had one specific transformation from u to v and another transformation s from v to w, then the composition S circle T will be a linear transformation from u to w, and the way we define it, usually we don't write this circle notation, usually we just write ST, and this ST composite transformation has the effect on u by first applying T onto u, and then once we are in V, we can apply S. So you get an element of W. And then again, it's some work to see that this is well defined, and also it's linear. And if you want to see something similar to matrix mapping, then the idea would be that if you have an n by n matrix mapping from Rn into Rm, then if you have a B matrix, which is, let's say, K by M, that means it maps from M, Rm into Rk, then the way you can combine together the two matrices is written as BA, because then you have sizes K by M and M by N, so these middle dimensions agree, and then the result will be a K by N matrix, so that means this will be a mapping from Rn into Rk, composite transformation. And then when you apply BA into a vector, it's the same as first applying A to the vector and then get a Rm vector, and since B is K by M, that means we can apply B, we can multiply with the matrix B to get a Rk vector. And of course, you should remember from basic matrix operations that matrix multiplication is not commutative in general, which is the same thing as saying that the composition of transformation is not commutative, but this is also kind of obvious since you are going between different spaces, so you cannot mix up the different spaces. It's easier to not pay attention to that when you have all vectors Rn, Rk, but if you have completely different vector spaces, that should be obvious. All right, so this is it for this section. I might create more examples based on requests.